What's up, guys? In this video, I want to go over graphing made easy by focusing on understanding how to graph as well as the characteristics of four main functions. All right, so the first one is going to be the quadratic equation. Once we get over graphing a line in slope-intercept form, we then put our attention to y equals x squared. Now, this is going to be what we call our U-shaped graph because it kind of looks like a U. And there's a couple important things that we need to kind of recognize about this graph. First of all, is that it has this kind of point, which we call the vertex. Now, in this parent graph, that is going to be our lowest point. So we have a vertex here at 0, 0, as well as points on this graph as over 1, up 1, which is also symmetrical of the y-axis. So this graph is symmetrical about the y-axis. It has a minimum point here at 0, 0, and as well as our points, or the behavior of this, is over 1, up 1, and if you over 2, up 4. But when we're going to focus on graphing, we're not going to focus on graphing using a table or identifying all the values. I want to focus on understanding what the parent graph looks like, one point in that parent graph, which in this case is going to be the vertex, 0, 0, and then go ahead and applying transformations. Now, if I want to shift this graph left, right, up, down, as well as apply some stretch and compressions, I'm going to apply some transformations. So that's going to come in a different form than our parent graph. That form is going to look like this. Now, this is like the foundation for all of everything we're going to do in this video, as well as for any other function that you want to. These values represent the transformations that we can apply to our quadratic graph. It's important to remember, a is going to be multiplying outside, right, of this x minus h quantity squared. So we're multiplying this a times x squared. That is going to be our vertical stretch or compression. The hk represents the vertex. So I can say the vertex is going to be h comma k. That's either going to be the lowest point, or if this graph was flipped, the highest point. So if I'm shifting my graph left or right, or up or down, that's going to come from my h or my k. Now, the last thing I want to kind of identify here is just a couple characteristics. I'm going to write down the domain and range, but then I'll kind of talk about these different functions. So let's go over the domain and range real quick. The domain, remember, is the set of all x values that make up this graph. You can see this graph is going to continuously expand to the left and to the right with no restrictions. So our domain is going to be from -infinity to +infinity, where our range is going to be the set of all y values that make up this graph. And you can see that this graph with no transformations goes as low as 0, but then it's going to continue up to infinity. So the range of the parent graph is going to be 0 to infinity. Now, if we want to impact this domain and range, then that's going to come from our transformations of h and k, as well as one other thing I forgot to mention. Our a is not only going to be a vertical stretch or compression, but it's also could be a reflection. If my a is negative, this graph is going to flip about to the x-axis. All right, now the next graph is going to be what we call our square root graph. Now this graph is going to look something like this. And it's important, again, we can still have the same common point of 1, 1. But the point that I want to focus on is, again, going to be the 0, 0. That's the easiest way for us to be able to move this graph left or right or up or down, whatever needs to be the case, based on the transformations. Now, here's the kind of kicker, ladies and gentlemen. The transformations of our square root function are the exact same over here. The only difference here is going to be what the function is. This is going to be x squared. This is representing square root of x. Now, in this case, we don't like to represent our transformations with h and k because in simple terms, it's not really representing a vertex per the definition that we used over here. So in this case, we're going to use a, b, c, and d. Now, you might be looking at this and be like, whoa, 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 what happened, Mr. McLogan? Well, what happened was I inserted in an extra value inside the middle. Now, a lot of times you can do the same thing over here. You can create a b in front of this case, but it's important to understand what exactly is this b doing inside of that function. Well, if a is your vertical stretch or compression, b is going to be your horizontal stretch or compression. For a quadratic, they're going to have a lot of the same similar facts because this is a graph that's symmetrical about the y-axis. Also, a is a reflection about your x-axis. B is a reflection about your y-axis. A lot of times we don't go over this or cover it in depth with the quadratic function because does it really matter if this graph is reflected about the y-axis? No, you're going to get the exact same graph. But when we start introducing this to the square root function, you can see that if I have a reflection about the y-axis, that's going to create a completely different graph. If I have a reflection about the y-axis, again, that's going to create a completely different graph. So it's really important when we are understanding not only our stretches and our compressions, but our reflections, we need to understand, is that being applied outside, which means it would be a vertical, Or is that going to be inside, which means it would be a horizontal reflection? Now again, understanding the C and D are going to have the same impact as our H and our K. A lot of students forget we introduce a new function and they forget what those transformations are doing. But again, always go back and revert to this standard form, because a lot of times it's much easier for us to remember what the graph looks like when it's represented as a quadratic. Now the next thing I just want to do is, again, let's just kind of review our domain and range. The domain in this case is the set of all values that make up our graph. So in this case, that is going to be from 0 to infinity. The range is a set of all y values that make up this graph. So in this case, that is going to be, again, from 0 to infinity. All right, so the next graph is going to be the exponential equation. And this one doesn't look like anything that we did before. But the same thing, guys, what I'm trying to reiterate to you is what we're going to be applying here is related to what we did here and is going to be related to what we did here. So again, I can take this equation and I can rewrite it with its transformations in mind. Again, we have an important point here. We have 0, 1. That represents the y-intercept of that equation. However, when we apply some transformations, that can change things. So, and we'll talk about that here in just a second, but I want you to see the relationship or the similarities between this equation, and that equation. Again, this graph looks nothing like the rest of these. We have a horizontal asymptote at y is equal to 0. We have an x-intercept at 0, 1, as well as this graph is going to be increasing here from on the whole part of its domain. Now again, A is, yes, going to be a vertical stretch or compression, but what's important about that is whatever A is, that's actually going to be my new y-intercept. So in this parent graph, you can see A is equal to 1. That's why the y-intercept is equal to 1. If A was 5, my new y-intercept would equal to 5. Now again, we also have to consider the other transformations, because I could have a C, which just like this one and just like this H is going to shift the graph left or right. Or I could have a D, which just like here and just like here could shift this graph up or down. So you got to make sure you're aware of it, but start with your A, your y-intercept, and then apply your transformations. A is also reflection about your x-axis, and B is that reflection about the y-axis. Now again, let's go and talk about the domain and range, because there's some differences here that we've had from these other two equations. So the domain in this case is going to be from -infinity to infinity, because all the x values are going to be defined for this function. The range, however, you notice is, again, there's no negative values, just like over here and just like over here. But the range in this case is 0 to infinity. And the reason why that's different is because I have a horizontal asymptote. See, here 0 is defined because that's the lowest point on the graph. Here 0 is defined because that's the lowest point on the graph. But here, as this graph is approaching 0, it's always going to be approaching 0. It's never going to be defined. That's why we use the parentheses here to represent the minimum point of our range. I couldn't spit that out. All right, now the last one is going to be our reciprocal function. Now this one is, again, one of those that just gets students confused over and over, because like we did with the last exponential graph, we have a horizontal asymptote, but now we're also going to be introducing a vertical asymptote. So we have a lot going on. We also recognize this graph is kind of like decreasing here from left to right. There's nothing going on here, and then it's decreasing again over here. The domain and range sometimes gets students tricked up with recognizing how to deal with these asymptotes or these undefined values, and then also recognize there's no real obvious point here that we are working with, and what the heck happened to the B in our transformation function? Well, there's something important that I want to kind of go back to, and I mentioned it for the quadratic, but I think I forgot to mention it for the square root function, and I know I forgot it on my exponential function. And that is all about symmetry. Notice how my quadratic function is symmetrical about the y-axis, right? This is what we call an even function. The square root function is not symmetrical about the y-axis, and it's not symmetrical about the x-axis or the x and the y-axis, or what we call origin, which would represent an odd function. If you reflected about the y and then reflect about x, you have something that looks like this, which is not the same graph. Therefore, it's not symmetrical about the origin. Same thing with the exponential function. And if I reflect and reflect, I'm getting a brand new graph. But what about this graph? If I take this graph and I reflect it about the y-axis, I'm now going to have something that looks like this, and then I reflect it about the x-axis, I get the exact same graph. That's critically important, because what that means is this graph is going to be what we call an odd function. It is symmetrical about the origin. So what that means is reflecting about the x and reflecting about the y is going to yield the exact same graph, right? It doesn't really matter if I say I want to represent A in the numerator and say it's a reflection about the x-axis, or if I think of A in the denominator and think about a reflection of the y-axis. It's going to be the exact same thing. So A actually, we factor back A out, and that is going to have the same impact if we thought about A as a vertical or a horizontal reflection. And the same thing can be said as we're going to think about stretching and compressing. So A and B is kind of redundant in this case, so we're just going to leave it as one coefficient. But I wanted to keep the C and D exactly where they were for these other functions, so we kind of have some similarities. We can understand, oh yeah, remember, x minus c, that's going to be shifting my graph left or right, and D is going to be shifting my graph up or down. Now, the last thing I want to go over with this is, again, just how to identify the domain, because this is going to be different than all the rest of these graphs, right? The domain was all real numbers, only positive numbers, all real numbers. Now in this graph, you can see that the domain is defined for all values except for equal to 0. So what we're going to do is find the domain from here to here, and then find the domain from here to here, and create a union symbol to combine them together. For this section over here, my domain is negative infinity to 0. For this section over here, my domain is going to be 0 to infinity. And again, 0 is not defined. That's why I'm using parentheses, because there is a vertical asymptote. For the range, that's going to be a set of all y values that make up this graph, which again, you can see going up to 0, it's now going to be undefined. So it's going to be negative infinity to 0, union 0 to infinity. So there you go, ladies and gentlemen. That is a quick little summary of all the kind of transformations, the domain and range, and the characteristics of, in my opinion, the 4 functions that you absolutely need to know. Because if you know and you are comfortable with graphing these 4 functions, I don't care what function I give you or your teacher gives you, you're going to have the tools for success. I wish you the best of luck, and I'll see you on the next video. Cheers.